Welcome to EdVantage. My name is Dr. Scott Adamson, and today's focus is on interpreting the meaning of a derivative in the context of a pretty real-world situation. You all can imagine purchasing gasoline. We do it probably weekly. So let's just consider a hypothetical situation. The number of gallons of gasoline sold, we'll call that the variable N, is dependent upon the price of that gasoline. We'll call that variable P. And we're going to name that function N, the number of gallons of gasoline sold, is a function of the price. Or we could say the number of gallons sold is dependent upon the price. And let's just suppose that we wanted to interpret the meaning of f prime of 2.899. Let's talk about what that means. But before we go specifically into that situation, let's just do a quick refresher on what a derivative is conceptually. First of all, from a previous video, we studied the limit definition of derivative. And what we said about that is this. We want to determine the limit as h goes to 0. Let's talk about what h means a little bit later, but let's first get into what this ratio is here. This says f of x plus h. Imagine this. At some input quantity x plus h, we're going to determine the output quantity f of x plus h. Keep that in your mind. We're also going to determine the output quantity for an input of just x. Imagine inputting a particular value for x and outputting f of x. And we want to compare those two outputs. Compare them, I mean, by subtracting. What's the difference between those two outputs? Now, this input of x plus h is the same as this input of x, just a little bit beyond. It's a little bit of h beyond x. So as h gets really, really tiny, what we're saying is input an x, input x plus a little tiny bit, and compare their outputs. How much more or less are those two outputs? That is, what's the change in the output? Now that change in the output is relative to the change in the input. Remember, we said start at some value of x, change just a little bit away from that value of x called h is approaching 0. So the change in x, the change in the input is that amount h. So this change in the output relative to the change in the input is what we're talking about when we have a derivative. Now, Gottfried Leibniz, the mathematician who is credited with inventing calculus, used the notation dy dx to express this idea of derivative. And the dy dx is saying delta, change in y relative to change in x. So connect it back to this. The numerator, the change in those outputs, Leibniz would call dy. The change in the input, that little change of h, Leibniz would call delta x, dx. And that ratio is going to determine the rate of change. So what I want you to be thinking about here as we go back to our gasoline example is, the numerator is having us focus on how the output of the function is changing. The denominator is having us focus on how the input is changing. So in our case, we have two quantities. N, the number of gallons of gasoline sold at a station. And we have another quantity, P, the price of this gasoline. And we said that the function is N is a function of P. N is the output, N is the dependent quantity. P, the price, is the input or the independent quantity. And so our function would graphically live in a coordinate plane like this. N is a function of P. And we're going to think about what would the derivative mean in this case. Now, first of all, let's just think about how this might work in the real world. Can you imagine this? The price of gasoline is 0. Free gas! We would probably have a lot of so-called sales, because the gas would be free, it wouldn't really be a sale, but we'd have a lot of gallons of gasoline sold at those prices. As the price of gasoline gets more and more and more and more and more, we might expect people to use less and less and less and less, and so in some way, shape, or form, we would see a function that would be decreasing. The more the price is for this gasoline, the less gasoline we're going to sell. So I'm kind of wiggling a function here, not to be specific of what this function formula actually is, but just to communicate the idea that as one quantity increases, the other quantity decreases. So connecting back to the derivative, what would this derivative mean? First of all, what does the 2.899 mean? Notice in our function notation, the 2.899 is our input quantity. So we're saying at a price of 2.899, that is $2.89, and look at those gasoline signs, it'll say $2.89 and 9/10. So it's $2.899 per gallon officially. At that price, the rate at which the amount of gasoline sold is changing is given by this derivative. That is, if we change the price, that value of H, that delta X we were talking about before, if we change the price by some amount, the number of gallons of gasoline will change by some amount. And in this case, if we change the price in this direction, increase the price, then the number of gallons sold will change in this direction, a decrease. We'd have a positive, we'd have a negative. And so what we would say is, first of all, this derivative could be interpreted as follows. At a price of $2.89 and 9/10, if you increase the price, the number of gallons of gasoline will decrease. So the derivative would have a negative quantity. Now, notice how the language is being used here. What we're saying is that the price is changing, causing a change in the number of gallons of gasoline sold. That idea of change has to be part of how you interpret the meaning of this derivative. And in this case, we would say that the derivative is negative. Let me just give you a little more practical example here. What if I just said that the derivative was negative 35? What exactly would that mean? Well, we could say this. If you increase the price by $1, then the number of gallons of gasoline sold would decrease by 35 gallons. And so the interpretation here would be, think of this as over 1. Increasing the price by 1, having a change in the input quantity of 1, results in a change in the output quantity of negative 35 gallons. So in terms of units, this would be gallons per dollar. At a price of $2.89.9, for every additional dollar we charge, we're going to sell 35 gallons less gasoline. That's what this derivative means. The important thing I want you to ponder on as you read the notes for this video, think about the language that emphasizes the rate of change. However you interpret a derivative, make sure that your language involves rates of change. This is a decrease of 35 gallons. The word decrease is a rate of change word for an increase of $1 in price. Now, we could interpret this other ways as well. We could say 35 over negative 1. That's still negative 35 in terms of the value of this derivative, but instead of thinking about a decrease in the number of gallons for an increase in the price, what if we reversed it? What if we decrease the price by $1? Well, if you go back $1 in price, then the number of gallons of gasoline sold would increase by 35. And so it's still 35 gallons per dollar. It's still negative 35 gallons per dollar, but we're just thinking about it in reverse. $1 cheaper, sell more gas. $1 more expensive, sell less gas. Overall, the derivative is interpreted as this rate of change, in this context, a negative rate of change. So study the notes, and as you are faced with different derivative contexts, make sure you're capturing the idea of how are these quantities changing, not just what the quantities are. Use words like increase, decrease, or just say change. That will help you to communicate what a derivative is really about.